Ever find yourself scrolling through those Netflix recommendations and, kind of marveling at how well they've got you figured out?
Yeah, it's a bit uncanny sometimes.
That's the power of machine learning, right? But what if I told you we could peel back the layers of that magic, make it something everyone can wrap their heads around, even if you don't speak fluent code?
Sounds intriguing. How do we even begin to unpack something that complex?
Well, that's where micrograd enters the scene. We're about to take a deep dive into this fascinating GitHub repository, and trust me, there's a reason it's been creating such a buzz. Imagine getting a peek under the hood of a self-driving car. We're not talking about fixing the engine here. We're talking about grasping those fundamental principles, the essence of what makes the whole thing tick. That's what micrograd does for machine learning.
What I find really captivating about micrograd is its remarkable simplicity. It manages to distill the very core of machine learning, this thing called an autograd engine. Have you heard of that?
Autograd engine, honestly, it sounds a bit like something out of a sci-fi movie to me.
Right, but it's actually pretty straightforward once you break it down. Imagine you're trying to teach, say, a self-driving car to stay in its lane. This autograd engine comes into play by calculating these things called gradients. Think of them as the subtle steering adjustments the car makes with each attempt, gradually getting closer and closer to that perfectly centered sweet spot.
And judging by the 40 forks and 481 stars it's racked up on GitHub, it's definitely struck a chord. This isn't just some obscure code snippet. People are paying attention.
It's like micrograd has cracked the code on understanding how machines learn. And the best part is, it's sharing that knowledge with everyone.
It's putting the recipe out there for all of us to see, which is amazing.
Exactly. And what truly sets this project apart is its commitment to clarity. It cuts through the usual jargon, making these concepts surprisingly approachable.
So you're saying you don't need a PhD in mathematics to appreciate the elegance of this code?
Not at all. It's designed to be accessible, even if you're just starting to explore the world of machine learning.
Okay, you've piqued my curiosity. Let's dive into this code and see what makes it tick.
Sounds good. Oh, at the very heart of micrograd, we find this thing called the value class. And now this isn't just about storing a number, it's about understanding its influence.
Hold on, so it's more than just a number on a screen. What's so special about this value class?
Think of it like this. Imagine you're baking a cake, right? And you want to know how much each ingredient contributes to its sweetness. This value class is like carefully labeling each ingredient, your flour, your sugar, your eggs, with its exact sweetness level.
So you know exactly what to tweak if you want to adjust the final flavor.
Precisely.
So we're not just storing numbers, we're cracking their impact, their influence on the final outcome. But how does micrograd actually do that? Are we talking about some seriously heavy-duty math here?
Well, that's where it gets really interesting.
Yeah.
You see, micrograd handles those basic math operations we all know, addition, multiplication, but with a unique twist. It's not just about crunching the numbers and getting a result. It's about simultaneously tracking how each number contributes to that final answer.
Okay, I think I'm following so far. We've got these value classes keeping tabs on every number's influence as they're being thrown around in the code, right?
Exactly.
So walk me through how this plays out in practice. Like, what happens when the code has to deal with, say, adding two of these value objects together?
Sure. So let's say we're adding two of these value objects. Micrograd will add the actual numbers, just as you'd expect. But here's the key difference. It also diligently updates that influence factor, that gradient for each value, essentially showing how each one contributed to the final sum.
So it's like having this running commentary, this log of how each number is impacting the overall outcome, even as those numbers interact and change.
That's a great way to put it. And what's remarkable is that this all happens seamlessly behind the scenes, thanks to some clever use of calculus. Specifically, there's this thing called the chain rule.
Uh-oh, calculus, now you're going to make me dust off my old textbooks.
No, don't worry. You don't need to dive back into calculus equations. Just think of the chain rule as this elegant little shortcut, a trick micrograd uses to calculate those influence factors, those gradients, super efficiently.
Okay, that's a relief. But I have to ask, this is where those activation functions come into play, right? I've heard the term thrown around, but never really grasped what they do.
They're absolutely crucial. They're what give neural networks that extra oomph, that ability to tackle complex patterns. You see, the real world rarely operates in straight lines and simple addition.
Right, it's messy.
Exactly. And that's where activation functions come in. They introduce those necessary curves and nonlinearities, allowing neural networks to mirror the complexity of, well, how our own brains process information.
So To use a metaphor, it's like the difference between sketching stick figures and creating a Van Gogh masterpiece. Those activation functions add the crucial details and nuances that breathe life into the whole thing.
Exactly.
But we're still missing a piece of the puzzle here. We've got these activation functions, all this intricate math going on behind the scenes, but how does it all come together to form an actual learning machine?
That's where the multi-layer perceptron, or MLP for short, takes center stage. Think of the MLP as the architecture of our learning machine, the framework that allows it to process information in a way that mimics the human brain.
So it's like the blueprint for our very own thinking machine, and it's all laid out right here in this code.
That's a great way to put it. Micrograd lays it all out in a very intuitive way, using these things called neuron and layer classes.
So we're literally stacking the building blocks of intelligence here.
Precisely. It's all about how information flows through those layers, from one neuron to the next. That's where the magic of learning really happens.
Fascinating. But this learning, this aha moment for the machine, it all boils down to something called the loss function, right? That's the feedback mechanism, yeah. So what exactly is that, and how does it work in the grand scheme of things? So we've laid out the blueprint with our MLP, but how does this thing actually learn? It's all about that loss function, right? Something about measuring how well the machine is doing.
Exactly. Think of the loss function like, a tough but fair coach. The kind who observes every move the model makes, how it's interpreting the data, and then gives very specific feedback on where it's going wrong.
Less, you got this, and more, here's where you tripped up.
Exactly.
Okay.
And micrograd uses a particular type of loss function called negative log likelihood, or NLL for short. Basically, it measures just how far off the model's predictions are from the actual data.
So the smaller that loss gets, the closer our machine is getting to really understanding the data.
You got it. And to really fine-tune that learning, to nudge our machine toward a low loss, we use something called an optimizer. In this case, it's the Atom W optimizer.
Atom W optimizer, that sounds a little intimidating, not gonna lie.
It's not as scary as it sounds. Imagine for a second trying to solve one of those really, really complex Rubik's Cubes. You can just keep twisting and turning randomly, hoping for the best, right? Or you could use a set of algorithms, a strategy to guide your moves. Well, the Atom W optimizer is like that strategy. It efficiently steers the model towards the best parameters, those perfect settings that minimize the loss and boost its accuracy.
Okay, so we're not just throwing data at the machine and hoping for a miracle. There's a real method to the madness. But can we actually see this learning process in action? Does micrograd give us a front row seat to how the machine is improving?
Absolutely. There's a section of the code dedicated to this. It shows how the model learns from the data in cycles, kind of like practicing a skill over and over again, making predictions, and then refining them based on feedback from that loss function.
So it's getting better with each attempt. And to make it even cooler, micrograd doesn't just tell us about this learning process, it actually shows us.
You got it. Remember those connect the dots puzzles? Micrograd uses something called a computational graph. It's a visual representation that shows us how all those dots are connecting as the model learns.
That's incredible. It's like we're watching the learning process unfold right in front of us. Who would have thought something as complex as machine learning could be broken down into such elegant, approachable code?
It's pretty amazing, isn't it? That's the beauty of micrograd. It takes a field that often feels shrouded in mystery and makes it accessible to anyone who's curious enough to take a look.
It's like we've been given this powerful engine, and micrograd is handing us the keys, inviting us to pop the hood and see how it all works.
And maybe even tinker with it, See what we can build when we understand the fundamental building blocks of AI.
Now that's an exciting thought. What happens when you empower a generation to really grasp the potential of AI? The possibilities are truly limitless. That's been a fascinating look at the world of micrograd. Until next time, keep exploring.